Okay. So today, the first topic we're going to talk about is we're going to look at auxiliary power units, also known as APUs. And these are covered, when we're looking in manuals and that kind of thing, you're going to find the information surrounding them in ATA chapter 29 or 49. There we go. So the auxiliary power unit is they're a small turbine engine that's in addition to the engines on an aircraft. So when you see, majority of transport aircraft today are twin engine. There's still a few 3 and 4 engine airplanes out there, but majority being twin engine. Referring to the main engines that provide thrust, there is in a twin engine, there is a third turbine engine that's not normally visible, and that's the APU. And so it is used most often on the ground for ground service purposes, providing electrical power. And then it can also provide electrical power as a backup or a secondary source in flight. Depending on the APU, it may be all the way up to service ceiling. Some of them, it might be limited in altitude. The other function of the auxiliary power unit, or APU, is to provide pneumatic pressure. And the most common uses of this are on the ground for engine starting and running the heat and air conditioning system. In flight, if there's an issue with bleed air coming off the engines, they have the potential to be used to continue to run heat and air conditioning, which also ties into the pressurization system. But typically they're limited to use on the ground, and then they're shut out. Once the engines are running, the APU is shut down, not started again until after the aircraft lands. However, it doesn't mean that it can't be used as a backup at times in flight. And so for pneumatic, though, oftentimes there's a limit to how high the airplane can be flying to use it as a pneumatic supply. And so if it does have to be used as a pneumatic supply, we did have instances where if a bleed system off of one of the engines wasn't working, the APU would be used as a secondary. We would have to limit how high we flew the aircraft. The last thing that it can be used for is in flight. If the engines do shut down, you can use the bleed air off the APU to attempt to do a restart. But again, that's at typically a limited altitude. So what it looks like is something like this. And here, this is an APU operating limit chart. It looks at airspeed. Most of the time for crew, we're going to be in that 200 to 300 knot range. So the normal kind of section here. You can see at altitude, up to 13,000 feet, you can use the APU for engine starting. Up to 15,000 feet, you can use the APU to provide bleed air. If you need to use it as a backup bleed air source in flight, the flight is altitude limited, 15,000 feet. The APU itself can be started up to 30,000 feet. And once it's started and running, you can operate it up to 37,000 feet. And in that range, above 15,000 feet, you can use it, in this case, to supply electrical power. So if one of your engine-driven generators wasn't operating, you could often use the APU generator, can be used as that secondary source to make sure you always have 2 generators online on the aircraft for dispatch purposes.
Wonder if there's a reserve volume for that.
APUs generally come in 2 categories, and it's based on kind of the engine size that or the aircraft size that it's going to be installed in. So this is an example of a smaller APU, and some of the things that you can see on there, some of the things that it's going to do is mainly to power what we would call accessories, and so those are it'll have a starter that runs off 28 volts, but it'll then have a generator that can put out 120 volts, 2 separate items. Some small aircraft, if they're a DC aircraft, they'll have a starter generator on them. They can run, then pneumatic is bleed air that we can pull off of the APU. And then in some aircraft, these also can be used to run a hydraulic pump as well, or a pneumatic pump to provide things like reservoir head pressure. And in the next unit, we'll look at hydraulics and we'll talk about where that's used. So here's the inlet on this. This is obviously a cutaway, but it's got the inlet kind of on the side. The air gets pulled into a compressor. It's centrifugal compressor in this case. And then it has a reverse flow combustion chamber. And then a turbine. You can see the turbine and the compressor are basically back to back. So the turbine spins the compressor. And it drives the accessory gearbox that's shown here on the left with those various accessories that go on there. So the starter here shown at the top, there's a fuel pump kind of in the front, and then a generator behind the fuel pump there. On larger aircraft, we have a slightly scaled up at APU, and it has similar components, but the way it supplies bleed air is a little bit different. So it still has an inlet. You can see it's fairly square, and that's a pretty common design in order to connect to ductwork on the aircraft. That goes into what's called the gas producer compressor. So the gas producer is the core of the engine. There's a combustion section, again, reverse flow annular with in this case, an axial flow turbine versus the last one that had a centrifugal turbine. But we have our turbine section here that's going to drive that gas producer compressor. And then on that same shaft, we have a second compressor that's used for pneumatic supply. And so this one, instead of taking bleed air off of the main compressor, it has the ability to produce dedicated bleed air. And these are teed together across the bottom. You can see basically ductwork and a valve that allows for alternate air. So let me I can pull up a pen here and kind of point out what I'm talking about. Hopefully this shows up. But with the pneumatic supply compressor being here, air can come out through this duct of the aircraft, or the bleed air that comes off of this compressor goes into the plenum. So before it goes through combustion, it can be routed out through this tube here. And then there's a valve at the bottom that can be used to switch between the pneumatic supply compressor using just the combustion section compressor in order to produce that bleed air. And so it'll depend on the amount of load, how much air is needed, and it can swap between those two different kind of modes of operation. So clear these and we'll move on. The APU is almost always, for most aircraft, is going to be installed back in the tail area somewhere. Now, some of you have done the APU lab on the 727, and that one is installed down in the wheel wells because it does have a third engine in the tail. But for most of your twin engine and four engine aircraft, the APU is going to live in the very back tail cone. So here we've got the tail of an aircraft. Aircraft would be off to the left. I kind of drew in where the vertical stab was. In the APU, it shows various ductwork, and then the APU itself being right in this area right here, with exhaust coming out the back and intake air coming in through a plenum at the top of the aircraft. And then there are a pair of access doors at the bottom. I've got some better pictures of those in the upcoming slides. There's that air intake door. Some airplanes have an air intake door, others just have a scoop that's open all the time. It just depends on the design of the aircraft. The inlet, the APU itself, and then exhaust coming out the very back. And so most twin engine and four engine aircraft, you'll see a small kind of a hole at the very back of the aircraft that is the exhaust duct coming right out the end of the tail cone. And then, like I said, some access doors at the bottom to be able to get to it. Other aircraft, instead of using access doors, have a tail cone that can be removed. So here's an example of an APU where the tail cone has been removed and it's exposing it. And what you can see on this one is the inlet. Here's that relatively rectangular inlet. Here's the exhaust that would be pointing out the back of the tail cone. And this is a smaller APU, so it doesn't have that dedicated compressor. It's just going to have a normal kind of the compressor that supplies both bleed air and air to the combustion chamber, and then a turbine. And then in this case, all the items it's driving are at the front. So generators, starter, fuel pump, hydraulic pump if it has one, are all going to be on that right side there. Some bigger aircraft a little further away, you can see the APU kind of tucked right above the horizontal stabilizer right here. An inlet door on the side just below the rudder above the horizontal stabilizer, and then the exhaust at the back. If we look at them more from a back angle, there's that hole at the very back of the tail cone that I was talking about. That's the exhaust, and then you can see the door sticking up again above there. In some cases, if the APU is a little bit further forward, here's an example of a plane where the APU is further forward. In this case, the APU exhaust is here below the engine. So rather than being located back in the very back of the tail cone, it's more in an aft equipment bay area. Again, this is not a super common design, but it is out there, and you'll see. And that's why you can see this big, behind that APU duct, that APU exhaust duct, there's a big gray rectangle. Those are all heat shields to prevent the side of the airplane from, the normal, those are titanium heat shields so that the aluminum underneath isn't damaged by the hot exhaust. Here's looking up at an APU that's in the tail cone. You can see this has the two doors that are open. So we're looking at the bottom of the tail right now. And at the front, there's a firewall isolating the APU from the rest of the aircraft. Every kind of APU and every turbine engine mounted on the aircraft has to be isolated from the rest of the fuselage or the wings by some kind of a firewall. It creates something called a fire zone. So the area inside of this inside this tail cone right here, behind this firewall, is the fire zone. And you'll notice that everything going through that firewall is some kind of a sealed connection. So cannon plugs right here have sealed plugs. The ductwork going through right here has a seal around it. The wiring, and then the fuel line, which the fuel line runs right along here. And it comes down, and it has a B-nut sealed opening going through down there. And the reason for that is this chamber, when those doors are closed, they also have a rubber seal on them that's shown kind of along this edge. So when those are closed, it creates a sealed compartment. And so if the APU were to catch fire, we can fill this space with halon in order to put it out using a fire bottle. So there's going to be, later on we'll look at fire prevention on the aircraft, fire prevention on the APU, and it has its own dedicated fire bottle in order to flood the space with halon to put out a fire if you were to have an APU fire. Here's that kind of same setup looking from the back, that APU enclosure. And this is showing the kind of the removal process they're using. In the industry are known as fishing poles. Can't imagine where they got that name. But these two poles kind of clipped up on each side of the APU, and they have a cable that they have a cable that hooks to the APU. You remove the mounting, and then the two technicians there sitting on each side will evenly crank out cable to lower the APU out of this enclosure. So rather than having to lift it from the bottom, they're kind of a temporary crane you can install from the top. And that's a pretty common setup, as using these fishing poles rather than trying to get a forklift in there or something like that. But as I mentioned, the real important part, looking at the tail here, this serves as the APU enclosure, creates that fire zone between the tail cone itself and the firewall at the front. So, moving into the control side of it instead of the APU itself, this is a pretty common modern control panel setup. You can see there's basically one switch to control the APU under normal operation. It has an off and on and a start position. So to run the APU, you turn the knob to the on position. You momentarily turn it to start. It is a spring-loaded switch. It'll snap back to the on position, and then the APU will start up on its own. It does have an emergency stop here as well that cuts off fuel and electrical going to the APU, as well as closes any fuel valves and pneumatic valves. However, it's not used during normal operation. It's used again in the event of an emergency. And the reason for that is in this case, if you take that master control switch, APU master control switch, and you move it to the off position, the APU doesn't shut down immediately. It's going to close the pneumatic valves. It's going to turn off the APU generator, and then it's going to run through a cool down cycle that typically lasts anywhere from about 1 to 2 minutes before it actually shuts the APU off. You know, and some aircraft up to 1 to 2 minutes. And so, you know, if there's an emergency and you need to shut the APU down, you don't necessarily want it to go through that cool down cycle and that power down self check and everything that it does. And so the emergency stop just shuts it off right now without running any of those checks or without cooling it down. But you know, if it's been under heavy load, if it's been used to run the environmental control system, and a lot of bleed air has been used off of it, if the generator's been fully loaded up, running power on the whole aircraft, and you hit the emergency stop, turbine engines don't like to go from running at high power, high load to not running. Can cause damage to the engine itself in the form of shock cooling and other things like that. So you want to unload an APU in a sequence over time, and so that's what the normal control does. But again, if there was an emergency, if someone was going to be hurt by it, or if it caught fire, the emergency stop option allows you to shut it off now. From an indication standpoint, here's a modern indication. We have an ICAS display. This is the ICAS primary page, for instance. You can see engine display gauges on the left. And really, there's very minimal APU information normally shown to the flight crew. It is outlined in red right there, and it's pretty much limited to the APU where it shows 100%. That's the RPM. So when you start an APU and it runs, it essentially comes on, it runs up to 100% full speed, and that's where it's going to sit. That's where it wants to stay. And then to the right of that is a temperature indication. On some older aircraft, they also had an oil pressure gauge. On a modern aircraft like this, the area that's black above this, right here, would be where messages pop up. And if the APU had a low oil pressure incident, it basically, you'd get a message that says APU low oil pressure. It wouldn't actually, there isn't actually a gauge for it. All you do is get a message that shows if something like that happens. This box over here to the right, this shows a couple different types of indication you may get there. So you can see if the APU gets up to 108% RPM, it's starting to get near an overspeed condition. It goes from a green to a yellow indication, as well as if you get a high temperature. You know, here, if it hits 985 degrees or higher, it'll turn yellow for the temperature because that's getting too hot. And then if you get to the critical speed or critical temperature, you know, 109% or higher for the RPM, or 1035 degrees Celsius or higher for the degree Celsius, those indications will turn red. And it doesn't necessarily happen at the same time. You know, it could be running at 100%. But for some reason get up to 1035 degrees. In that case, only the temperature one would turn red. So it's, you know, the item that is being exceeded is what would change color on an ICAS display like this. And there's also typically messages indicated with the red, or, you know, some of these high temp, high RPM conditions. Looking at a physical panel, you know, if we look at an overhead panel, this is going off memory, this is out of the 757, I believe, 757 or 767. But on this entire panel, here is the entire APU control panel you have. It's got an indicator light, an emergency stop, and then it's got an off, on, and start switch, just like the drawing of the panel I showed you just before. And the indication on something like this, again, might just be some gauges, an RPM gauge, EGT gauge, temperature gauge, possibly an oil pressure gauge. In the event of an emergency, I mentioned when we were talking about the fire zone and how we have to be able to isolate it, the APU has its own dedicated fire bottle. This is an example of a fire fire control panel where it's got cargo fire bottles on the top and then an APU fire bottle on the bottom. There'd be another panel with engine stuff on it. But all you do, flip up a little, there's a guard over the switch so it doesn't accidentally get activated. You flip up the guard, push on the switch, and that will activate the APU fire bottle. And the way you get an indication is that APU button will light up red. You'd also get an APU fire message on an ICAS display or an ECAM display. But when you push that button in order to discharge the fire bottle, it's going to discharge the fire bottle. At the same time, it's going to shut off the generator because we wouldn't want a failing generator to potentially damage other electrical equipment on board the aircraft. And it's going to close the APU bleed valve so that we don't send smoke through the pneumatic system into the aircraft. It'll close the fuel valve for the fuel line going to the APU, so we cut off our fuel source to prevent the fire from continuing to grow. And then it'll discharge the fire bottle, which is halon, will displace oxygen inside of that fire zone. Under normal operation, APU fuel and power, the fuel comes from the main tanks. It doesn't have its own dedicated fuel tank or anything like that. It typically comes from one of the wing tanks. But it does have its own dedicated fuel pump that runs on 28-volt DC. And the reason for that is when we talk about fuel, most of our other fuel pumps are going to be AC motor pumps. They're going to be driven by the AC system. But the APU is used to start the engines. The APU is used to start the aircraft when it's all shut off. And if you don't have ground power available, you use a battery to start the APU, and then you use the APU to start everything else. And so we have, the APU itself is able to run off the battery. The APU starter runs off the battery. It's 28 volt, and then the APU fuel pump is going to be 28 volt, and that way we can run everything to get the APU going off of the battery until once the APU is going, we'll start the APU generator and energize the AC electrical system. During starting, the fuel valve is going to open. The boost pump is going to be DC powered and powered up, and the APU often does have its own battery and dedicated charger, although that battery can often be tapped by the electrical system as an emergency battery. So in flight, if we do need to use a battery backup, it often is the case that the APU battery can have power pulled from it in order to power other systems on the aircraft during an emergency. The start process, as I mentioned when we looked at the panel, there's not a whole lot to the control sequence. You have a switch that has an on or a start. When you move it to the start position or you press, some aircraft have two buttons. They basically got an on, like an APU on button and then a start button. But when you engage the start sequence, most APU are going to be automatic. Even the one on the 727 still used a simple logic card and didn't require any kind of crew member input other than pressing the start button to get it up and running. From there, if it has an inlet door, it'll open the inlet door. If it doesn't, then if it has just a scoop and it's already open. Your fuel valve and your DC fuel pump are both the fuel valve is going to open, DC fuel pump is going to start running, so it's going to send pressure to the APU. However, it won't go in yet. We have a fuel control on the APU that'll do that. It's going to engage the starter to get the APU spinning, rotating, and then it also will engage the igniters. It'll turn the ignition on. However, at that point, no fuel is actually entering the APU. The APU has to get up to a minimum, there's a minimum speed it has to be rotating at before we start to add fuel to it, because we have to have airflow through it since it's cooled by the internal airflow. Once the APU gets up to that speed, then the fuel control will energize and it'll open the solenoid valve that allows fuel to flow through the fuel nozzles. And then the APU will light off. It'll light off, it'll get up to a self-sustaining speed, and once the APU is self-sustaining, which isn't necessarily 100%, but it's on its way up to and accelerating, the starter and the igniters will disengage. and then it'll basically continue until it reaches 100% RPM. Again, that's all pretty much automatic after you hit the start button. This is just kind of a graph that shows it over time. So along the bottom, we have this instance, this APU happens to have two buttons. It has basically an on button and a start button. So the on button is pressed here, and the aircraft batteries here. The APU on button is pushed here. When that button is pushed, or when you move the switch to the on position, the APU ECU, which is the electronic control unit, it's kind of like the little FADEC that powers it, will power up. If it has a door, it'll start to open. And then when you go to the start position or press the start stop button, that's going to start rotating the engine, getting it up, RPM. It'll turn on the fuel pump, but again, fuel will not go into the engine yet, and the ignition will come on. After it lights off, then the fuel started there. Fuel gets put into the engine at 10%. It lights off. It gets up to 50%. Starter cuts out. It continues to rise. When it gets up to 99%, it's considered fully started. And that's when APU bleed air and generators become available. And so that whole process here, you can see they don't give a time, but it takes roughly 45 seconds or so, 30 to 45 seconds. So the bigger the engine, the bigger the APU, the longer it takes, just because you got to get it up to speed. So really, the APUs themselves, it's pretty simple in their design and their operation. There's not a ton to them. For detail, we'll be looking at turbine engines in more detail, and they almost kind of work like a little turbo, almost like a little turbojet or turbo shaft, where the whole point is to create energy to have that pneumatic supply and drive your generators. So that is the super long APU lecture. Any questions on that one?